Okay, welcome to Dynamical Systems Lecture 7, I believe. So we're going to continue today with looking at our two-dimensional dynamical systems, linear, as we started the last time. And I'm going to continue looking at the examples of what is possible in the phase space diagram. Remember in the last lecture, in the previous one, we gave the analytic results, where we computed the eigenvectors and we computed the time dependence that depended on an exponent of the eigenvalue. And then we basically, you can write down a solution in this form that's basically a constant times the e to the eigenvalue times the eigenvector plus a constant times the other eigenvectors. And I said there were three cases, and this is an example of one of the cases. And so what I'm going to do today is systematically go through the other examples you can find and then summarize everything that's possible on one slide. And so what I'm going to do next, what we did the last time was the saddle, which is where you have one positive eigenvalue and one negative eigenvalue. And what I'm going to do today is go on and do something that we call a stable node. So what happened there? I apologize. We're going to have this super quick tour. I have no idea what happened there. This is not what I was planning to do. Okay. So what I'm going to do now is give you another example, same technique, but what it looks like in phase space is dramatically different. In fact, this is an example of the first case. When I analyzed the possible cases you could get, this is an example of the first case. So once again, you get one of these problems, you don't know which case you have, and we go about it exactly the same as what I did in the previous case. You write it, you identify from your differential equation what your matrix or your linear matrix A is with constants. You immediately work out the determinant, which is 100 in this case, so that is minus 8 times minus 17 minus 36. And you work out the trace, which is just the sum of those two, and that is minus 25. Okay, you can immediately see the determinant is positive, so you know the signs of your eigenvalues are the same, and you know the trace is negative, so both your eigenvalues are going to be negative. So you know from that your solution is stable. Okay, and then so that's the next thing, you just write it down, the stable fixed point at 0, 0, and the next step is you work out the characteristic equation, which is just the determinant of A minus I lambda, and you get this thing. You can then go about solving it, and you can basically, by factoring this thing or by using that equation that I gave you in the last lecture, you get that lambda 1 is minus 5 and lambda 2 is minus 20. So always go back, check, make sure it corresponds to the fact that you have a stable fixed point. If from this equation you don't get two negative numbers, you know you've made a mistake somewhere. You then go back and you compute the eigenvalues. It's once again 1, 1 if lambda is equals to minus 5, and 1 minus 4 if lambda equals to minus 20. And then you write down the general solution. So there's sort of a recipe for linear systems, and you can get it basically e to the minus 5t times your eigenvalue, eigenvector plus c2 e to the minus 20t times your eigenvector. And what you can see is the time dependence here is very strongly, it's a negative exponential. So the moment your time gets anywhere above 0, it very rapidly, this coefficient here goes to 0, and you can see your solution is going to shrink to the origin. Okay, and that's what I mean by stable, right? Almost any solution almost immediately goes to 0, 0, or not immediately, with a certain decay rate goes to 0, 0 because you have negative eigenvalues. And then you once again go and you say, this is the general solution. We now want to find the solutions through a specific point, x0, y0. You say, how do I do that? It's easy. If time t equals to 0, these guys, the exponents are just 1, and so you have that x0 is equals to c1 plus c2, and y0 is equals to c1 minus 4c2, and you can invert that and then get what they are in terms, what c1 and c2 are in terms of x0 and y0. And so you can then, for any point, suppose you want to draw the trajectory through any one of these points, you can therefore just choose the points, work out what these c's are, and then put them back into the equation, and you have the expression for that particular curve going through that point. Okay. And the last time I said, when I drew that phase diagram, I said the first thing I always do is I go and pick a few xy points, and I actually draw the arrows so that I can check that the curves that I draw have these arrows tangent to them. And then I computer generated all of them, which you won't be able to do in a test. And so the one thing that I can say when you do that is, when I draw my phase diagrams like that, I usually choose to pick arrows or draw my first arrows on what we call null lines. So there's a special curves in your phase diagrams that are not your eigenvectors, but they're curves where you know x dot is equals to 0 or y dot is equals to 0. So when x dot is equals to 0, you know all your arrows are vertical, and when y dot is equals to 0, you know all your arrows are horizontal. So that makes it easier. So I go up to the top and I say x dot is equals to 0 on the line y equals to 8 over 3x. So I draw that line in, and I know then that all the arrows I draw on that line are either pointing up or down. And the same thing with y equals to 0, y dot equals to 0, that's equals to 0 on y equals to 12 over 17x, and I go and draw in that line, and then I put the arrows on it. Okay, so the null line is when y, those are the two that I've just mentioned, and what I'm going to do is I'm going to put in the vector arrows on the null lines. So when I'm drawing the phase diagram, the first thing I do is I put my axes on, then I put in the line where x dot is equals to 0, which is just this 8 over 3, and then I put the arrows in on that line, and I just pick a point on the line, and I basically know all the arrows must point down. It just is a question of how big they point down, how big the arrows are, and that I get by picking a point and evaluating what y dot is. And I can see, therefore, when y is positive, y dot is negative, and when y is negative, y dot is positive. So it becomes very easy to draw a whole bunch of arrows on that line. And then the same thing I go in this other point, the other null line, is when y dot is equals to 0, and so I draw in that line, and I know when y dot is equals to 0, all the arrows are basically pointing either in the positive x or the negative x direction, and I just pick a point on y dot equals to 0, and I draw in the arrow over there. So here I have that if x is positive, y dot is negative, and sorry, if x is positive, the arrows on the y dot equals to 0 line are negative, they want to move that way, and when x is negative, x dot wants to increase, it wants to move that way. So this immediately gives you an idea of what the flow is going to be like. So whenever I have a point on this line, I'm going to be flowing vertically up. And if ever I have a point on that line, I'm going to be flowing horizontally in. So you have, interestingly over here, you have two lines, and you know everything's going to flow into that area between the two lines. So you can almost guess that one of your eigenvectors are going to lie between these two lines. Okay, and that's true because 1, 1 does in fact lie between those lines. So the first guess I have for putting on arrows is always just to plot the null lines, and they're very easy to plot because I can get it straight from the differential equation without any analysis whatsoever. Okay, so that's what I do. The next thing I then go about doing is, this is just to give you a feel of what everything, the rest of the vector field looks like. I don't expect you to draw it, but I do expect you to draw the vectors on the null lines. And here you can see that all the vectors flow in, and then there's this special, remember I said that one self-contained line that the vectors don't go off of. There you have it, and that's your 1, 1 eigenvector. So the thing I want to emphasize is when you look at these phase diagrams, there's a logic to them. There's like a flow field, and it makes sense. And when you draw them, make sure that the thing is consistent in the sense that make sure when you've drawn the null lines, which are easy not to get wrong, and you have the arrows pointing a certain way, and you've then computed the eigenvector like 1, 1, that it makes sense that it lies between it. Okay, it's just a logical check, and it'll save you a lot of marks and a lot of errors if you just consistently try and get the arrows on the whole picture to make sense to you. Okay, so what I want to do next is I want to draw in the eigendirection. And now when we're looking at a node or a stable node, that meaning a problem in which both the eigendirections or the eigenvalues are negative, you basically have two types of eigendirections. You have what we call the slow eigendirection, where the absolute value of the eigenvalue is closest to 0. In other words, here, -5 identifies which is your slow eigendirection. Okay, and why that becomes important is that if you look at the solution, this one is going to decay a lot faster than this one. So when time gets larger, eventually it looks as if the solution approaches the origin along this one, and that's what I mean by the slow eigendirection. So it plays a more important role in your solution when time gets bigger. Okay. The other one that I'm going to plot is what they call the fast eigendirection. So that's the eigendirection where your eigenvalue lambda 2's norm is bigger than your slow eigendirection's norm. And you can see it's an eigendirection because all the arrows remain on it, but the arrows are also larger. Okay. And so you can now see, if we start plotting in the trajectories, what typically happens is when the time t is small, it approaches it comes parallel to the fast eigendirection. It comes along until it hits one of these null lines. It goes horizontal, turns around, and then approaches the origin along the slow eigendirection. Okay, another trajectory is just to say that it's mirror image. Here we are once again going parallel to the fast eigendirection. We hit a null line, and then we approach the origin via the slow eigendirection. Here is another one. We go closer. If we go closer to the fast eigendirection, it's the same thing. Once again, parallel to the fast eigendirection as when we start, and then as time gets larger, only the slow eigendirection remains, and we basically approach the origin over there. Okay, here you can see from this other side is once again parallel to the fast eigendirection, even though you're far away from it, until eventually you hit the slow eigendirection, and then you approach the origin. So you can see, you can almost immediately draw what the trajectories are going to look like, once again without solving them, simply by observing that when it starts, it's parallel to the fast eigendirection. When time gets large, it approaches the origin via the slow eigendirection. Okay? And whenever it hits one of these null lines, you must make sure its tangent is horizontal for the y dot equals to 0 null line, so it's going to turn around there. And when it hits the null line, I don't have one. I didn't actually draw one. So, for example, if you were to come from here, you would once again be parallel to C2 till you hit the null line and you're vertical, and then you bend in and go to the origin. Okay, so there's a logic to these things that you're going to start understanding more and more as you draw them, and I strongly encourage you to do that with the next problem set that's coming. Okay, so we've done a saddle where the two eigenvalues are different. we've done a node where the two eigenvalues are the same. The interesting thing, and this example is a stable node. Now, if you have an unstable node where the two eigenvalues are positive, that means it's basically going to go away from the origin. The picture looks almost exactly the same, except that the arrows are reversed, right? Because switching your sign of your eigenvalues, you can also get by switching the sign of t. So you basically run backwards if you have one with positive eigenvalues. So you're going to be running away from the origin. Okay, so here I just wrote down, this is an important feature. As t goes infinity, the trajectory approaches the origin, tangent to the slow eigendirection. As t goes to minus infinity, the trajectory approaches or goes parallel to the fast eigendirection. So that's a major feature of your stable node. Now, why does it keep doing that? Let's see if I can. Sorry, I don't want to go through. Okay, so what I'm going to do next is the degenerate cases. So if you remember, a degenerate case is when that thing under the square root was 0 and your two eigenvalues are the same. So your degenerate case is when your trace squared is equals to 4 times delta. Okay? Then your eigenvalues are the same and they just equals to the trace over 2. And a degenerate case can be stable if that thing is negative, if tau is negative, or unstable if it is positive. So let's look at one example, and this is the classical example, is if A is simply your eigenvalues on the diagonal, then both the eigenvalues are the same and they're equals to lambda. Your determinant is lambda squared and your trace is 2 lambda. Okay, and then the stability of the fixed point depends on the sign of lambda. And you can always get 2 eigenvectors, so this is not a degenerate case in the sense that you have just one eigenvector. It's a degenerate case where you have the same eigenvalue, but you have 2 distinct eigenvectors. So here you have xc1 is equals to 1, 0, and you have xc2 is equals to 0, 1, right? Both of these will solve your eigenvalue equation. They are linearly independent, and so you can actually write down the solution in the general form of basically x of t is equals to x0 times e of t. Okay. And y0 is equals to y0 times e of t. So this is just, this particular example is just the degenerate case which is diagonal. So your eigenvalues are just 1, 0 and 0, 1. Okay, and what that thing is that if you pick any point, it's just going to, if lambda is less than 0, it's just going to flow into the origin along that point. And this thing you can see we could call a stable star. It's an example of a degenerate node, but it's just where the eigenvalues are 1, 0 and 0, 1. So it basically flows in to the origin. And similarly, if you have lambda greater than 0, the thing is going to flow out, right? So this is where I said if you have an unstable node, the arrows simply flow out. Okay. So that's your one degenerate case. Your next degenerate case, or rather, let's go for another example before I do the next one. Let's look at another example of a degenerate case, namely this one. And so for this particular example, it's not obvious that it is a degenerate case to start with at all. So what you basically do, once again, you work out your matrix, you work out your determinant, which is 1, you work out your trace, which is minus 2, and then you actually go and check whether these things obey that equation. And you can see they do, because minus 2 squared is equals to 4. And when that happens, you basically work out your eigenvalues, and you see that both of them are minus 1. So here you have the case where you have two eigenvalues that are the same. Both of them are -1, so you immediately know that your thing is stable. In other words, the arrows are going to point to the origin. But where it becomes more interesting is that because they're the same, it's degenerate. But when we start now working out what our eigenvalues are, we're going to use this matrix. The first what our eigenvectors are. The first eigenvector is C equals to 2, 1, right? You can see that that satisfies B times C is equals to 0. But you also know that there's nothing else that can do that, right? So there's only one solution to B times C is equals to 0, and that solution is parallel to 2, 1. Okay, so this is a case where it's degenerate in the sense you have two eigenvectors are the same, but you can only find one eigenvalue. Okay, so this is the case where we had that special case that we did when we did the theory, where we actually have to construct the next eigenvalue, the additional vector, so that we can write two independent solutions. And to construct the next one, we have to find C prime, your next vector, so that B times C prime is equals to C. And you can show that to do that, you only have to find one that works. If you have C prime equals to 1, 0, then you can see that B times C prime is going to give you C. So then we've got an additional vector. So this thing is just a linear algebra problem that you have to solve. You have to get your second vector, and then you can construct your general solution, and it's basically what we've been used to with a 1 eigenvector, so it's just e to the minus tc1 times 2, 0. That's the normal one we're used to. But now we have to add back that other term. Remember, we constructed it out of C2 times e to the minus t times your new vector that you've constructed, this C prime, which is over there, plus t times the old one. Okay, and 2 lectures ago we proved that this thing would actually solve the differential equation, and it does. Okay, and we know that this second solution is independent from this first one because it's got a t multiplying that factor in front. So what does this solution look like? In some sense, we can imagine, we know what a node looks like. We would think that it is very similar to the node that we did, the stable node that we did in the previous example, but this t does something weird. So I'm just going to plot the phase diagram for you, and you're going to see that it actually doesn't do that much weird. In fact, it's a transition between this one and the previous case that we had. Okay, once again, to get the specific solution through x0, y0, you do the same thing. You simply say at times t equals to 0, y0 is equals to c1, right? Because that thing is 0, this thing vanishes, so it's y0 is equals to c1, and x0 is then equals to 2 times c1 plus c2, and so c2 is simply equals to x0 minus 2y0. Okay, so we now have the full solution with our constants are given in terms of the initial conditions. Okay, so let's once again plot it in the phase plane, and let's see what happens. Once again, you plot your null clines because you want to get an idea of what the arrows are like. So x dot equals to 0 when y is a quarter x. Okay, so that's what I've plotted over there. And you put the arrows on them. So here on the positive x side, it goes up. On the negative x side, it points down. And then you also plot y dot equals to 0. So you there have y equals to x over 3. So it's very close to the other line. And then you put your arrows in, and they're either going to point left or right. So here they point left. Over there they point right. So you can almost see that if you have something going in, it's sort of going to go in and cross the second line and go around like that. So it's sort of going to make bends over here at your null cline. The next thing we do is we plot in, just to give you a feel of what, if I were to plot all the arrows, you can sort of see this feeling where it's going to go round and bend at the null clines over there. The next thing I do is I'm going to plot in the eigen direction, but only the one eigenvector, the real eigenvector I have, because I know it's stable, so along this line, things are just going to approach the origin and they're going to remain on the eigenvector. So what is interesting now is that if we start putting in the trajectories in for this degenerate node, just if you're interested, this is where the other eigenvector comes in, but it's never that important in the solution. I've just put it in for for interest's sake. Okay, so what's going to happen is the trajectories are going to approach parallel to XC, right? Because over here, when time is small, it's basically this thing is going to dominate everything else, right? Sorry, when time gets large, this thing is going to be dominant, and this t times 2, 1 is going to be dominant. So the trajectories are always going to approach the origin parallel to this line XC. Okay. When they initially start, they're also going to go parallel to this line XC. And so what's going to happen is they're basically going to come in parallel to XC, hit one of these null clines, make a turn, and then come back in and approach the origin parallel to that thing. So if we start drawing them, you see here they go, they parallel to XC when t is negative infinity, and then they hit these null clines, they turn around as the arrows indicate, and they come in parallel to XC over there. And similarly with the other one, if they go like that, they are going to go parallel to XC, hit the null clines, bend and come back. And the same thing is going to keep happening over here. Okay, so this degenerate node looks very, very similar to the ordinary node. It's just that the structure of the solution is different in the way you write it out. Okay. So I hope you're getting a feel for what these solutions, even though they are algebraically very much the same, in phase space they have distinct meanings. Right. Now comes to the interesting thing. What happens when this thing, the thing under that square root goes negative? Okay. And you get a very different state. In fact, when the thing under the square root goes negative, you have complex eigenvalues, right? So just a reminder, your eigenvalue in 2 dimensions is just given by this expression where you basically have your trace, but under the square root you have the trace squared minus 4 delta. So when your trace squared minus 4 delta is less than 0, you can easily construct a matrix that does that. The interesting thing is, even though these eigenvalues then become complex, you can still get valid solutions. Okay, so normally what happens if something under the square root in dynamical systems gets complex, I'm like, we're looking for real solutions, don't go there. But when you're actually working out the solutions and you have complex eigenvalues, you simply have to combine it in a way that you actually get a real solution. So what I'm going to do is I'm going to go through the derivation in more detail than Strogatz does. He just uses it, but it's useful to actually see the full derivation slowly, so I'm actually going to do it for you now. So suppose we have a complex eigenvalue, so lambda 1, 2 is equals to the trace plus I omega, which is given over here, and I omega is simply, omega is simply equals to, minus omega is simply equals to that thing over there. So it's equals to omega squared is simply equals to the thing in the square root over there. Okay, so you have omega equals to the square root of delta minus tau squared over 4. So omega is a real number, and we've put all our imaginary possible difficulty into the I over there. And what happens when you get that, you can actually work out, you have complex conjugate eigenvalues, in other words, there's plus minus over there, and you're also going to have complex conjugate eigenvectors. Okay, and it's going to turn out that when you combine these two facts, you're actually going to get a real solution. And its form is going to be a little bit different to the general form we've been looking at, but it can be derived from there. And that's the derivation I'm going to do now. So I'm going to write the complex conjugate eigenvalue, I'm going to write in this way. Okay. Sorry, the eigenvector I'm going to write in this way. And the other eigenvector, xi star, is just you replace minuses in front there. And so then I go on and I write down the general solution just as the way we've derived it. So this is one of the happy circumstances where whether you're dealing with imaginary or not, you still, the formalism that we did in the previous two lectures is still entirely valid, except that the constants are now complex conjugates of each other. So here we go. So this is a constant, which is a complex number, times the exponent over here, times c, which is complex, plus it's the full complex conjugate of the first thing. So we still have two independent solutions. This thing is real over here, but it's just not as easily apparent as what it does. Okay, and that's what I want to make clear now. So the C is a complex conjugate constant, so we still have two basically independent solutions because we have two constants. The way we've written it down is just a bit mixed with each other. Okay, and now the initial conditions, we're also going to have at times t equals to 0, we're going to have that x of 0, we're just going to denote x0, and we're going to call that, we can immediately write down what it is. So at times t equals to 0, right, we have that x0, this is a vector, is equals to c times xc plus c star times xc star. Okay, and we're also going to have that at times t equals to 0, we have that x dot is equals to a times x0, and if I write that out, x dot, okay, and I simply take the derivative of this thing, I can get this expression. So I'm going to have c times this exponent times xc plus c star times that thing times xc star. And so what I'm going to do now is try and replace c and c star in this expression directly with the initial conditions. Okay, and it's going to make the answer, the general solution, a lot easier in what comes. So I've basically gone and I've massaged this thing over here a bit. So I have that a of x0 is equals to tau over 2 times x0. And the way I got that was to observe that this first term over here is just tau over 2 times c times xc plus tau over 2 times c star times xc star. So it's that thing over there. So that's where this term comes from, plus I omega times c xc minus c star xc star. Okay, so those things are still equal. And if we now go back and we say, let us recall this expression for our complex number of e to the I omega t, that is just cos of omega t plus I sine of omega t, what I can do is write down the general solution. Okay, so I now have two expressions over here for the constants and the eigenvector, multiplying the eigenvectors. And what I'm going to do is I'm going to use this fact to expand what this general solution actually does. So the first thing I'm going to do is I'm going to say this first term is just e to the tau over 2 times t, which is that term over there, times c times cos omega t plus I sine omega t. And then the second term is just e to the tau over 2t, c star, times e to the minus I omega t, which is just that. Okay, and then I'm going to group the terms of cos omega t and sine omega t together. And what I then get is very convenient, because it allows me to replace these constants that have been abstract constants and associate them directly with my initial conditions. So if I group cos omega t, take everything in front of cos omega t, I'm going to get that exponent plus c times the eigenvector plus c star times the other eigenvector. And I immediately know that this is just the initial condition over here. And over here, I'm going to do the same thing for the sine omega t term. I take out this e to the tau over 2t sine omega t plus I times this thing, which I can use the second equation to relate to the initial conditions. And that is simply just sort of ax0 minus tau over 2x0, okay, divided by I omega, but you've got an I over there, so the I cancels. And when you do that, you get that the general solution, if you have complex eigenvalues, is simply e to the tau over tau t times cos omega t x0 plus sine of omega t times a over omega plus tau over 2 omega I times x0. Okay, so when you're dealing with complex numbers, this or complex eigenvalues, you could either use this expression for the answer, or you can go systematically through and actually derive it again when you work with a solution, if you only want to remember this, this general result. So both of them are fine, but it's interesting to just see how you actually, the solution you get is a real one that's dependent on the initial conditions and this funny sort of funny reorganization of the initial conditions. And their time dependence is basically sine omega t, cos omega t, so it's going to oscillate. And it's going to either grow if tau is positive, or it's going to decay if tau is negative. Okay. And so what we're going to do next is look at an example and look at what it means for us in phase space. So once again, it's very hard to tell just from the equation what the system does. You've got to get the matrix A, compute its determinant, compute its trace. Okay, so 2 minus 2. And then you've got to check. Okay, so your characteristic equation here is lambda squared plus 1. So you know that your eigenvalues are I and its complex conjugate minus I. You can work out the eigenvectors. So here they are. It's basically, and you just treat them as complex conjugates of each other. So you have 2 minus I and 1, and its complex conjugate is over here. You can go on, then write down the general solution over there, and then you can simplify it, write it out, try and simplify it. Some of these are actually easier to simplify directly than remember the one that I derived, but both eventually get to the same result. So if I write it out in full here, you can immediately see that I can just combine the real and imaginary parts, and I can get that the initial condition fixes C1 and C2, or C and C star, by the condition that x at times t equals to 0 is simply this thing. So I simply replace t equals to 0 in here, and I then write down the expressions for the x term up at the top, which I've given there, and the y term at the bottom. So I now know that y0 is just c plus c star, okay, which is basically 2c1. So I have that y0 is equals to 2c1. This thing, I substitute in what this complex number actually is, and I get that x is equals to 4c1 plus 2c2. So I can solve this equation basically for x and y, and what I basically get then is that c1 is y over 2 from this equation, and c2 is related to x0 and y0 up there, and I can then go back, put these things back in there, and write down this expression for the answer. Okay, so this, whether you go and you use the general result or you derive it again yourself, in fact, I encourage you to do it both ways at least once. It's fine with me. So you can see this thing basically oscillates in time in cos of t, and oscillates in time. So your x component oscillates in time, your y component oscillates in time, and now let's try and actually draw what happens. So what this thing actually is in the phase plane, and it's true for any time you have complex numbers, is that you can no longer draw the eigenvectors in the phase plane, but it does oscillate either in the terms of an ellipse or in terms of a spiral. So let's just draw the first one, and then I'm going to stop there and continue the next time. Okay, so to draw this thing, and this is where it becomes important, you no longer have eigenvectors you can draw. So the first thing you draw, once again, is the easiest thing. You draw the null lines. Okay, so when x dot is equals to 0, you have that y is equals to 2 over 5, and you put in the arrows. So you can immediately get some feeling of what the flow, it sort of wants to go around that way. If x dot is equals, if y dot is equals to 0, x dot is equals to, y is equals to x over 2, and you draw the arrows in there. So what's going to happen here is, here the thing wants to flow to the right, then when it hits this x dot equals to 0, it wants to flow down. So you can sort of get the feeling that it wants to make a loop over there. Then the next thing I do, because I don't have the eigenvalues or real eigenvectors, I actually go on the axes, because that's also an easy place to actually draw arrows in, right? Because I can immediately say, let me put y equals to 0, then I can see, oh, x dot is like minus 2x, and y dot is like minus x, and then I can immediately see that here they point, when x is positive, they point that way, and when x is negative, they point that way. So I draw that in. I draw in the arrows on the y-axis, and then, because I know there's no trace, I'm basically going to have the circles closing in on each other. And so if I then go and plot all the arrows, this is just to give you a feel of what all the arrows are, but you don't need them. Okay? If I then go and I plot what the trajectories are, namely I plot what this parametric solution actually gives me, I get closed circles. And as long as tau is 0, you will always get, and you have complex eigenvalues, you will always get a closed ellipse. Okay, if you plot the others, they all go that way, and the thing that you must make sure of is that your ellipse basically follows the arrows that you've plotted in over here on your null lines and on your axes, and you can see it closes around like that. Okay, so if tau equals 0 and your determinant is greater than 0, every trajectory is closed. We call that a center. And I'm just not. Okay, and we call that a center. And I'm going to stop there for now. I'll look at the next example on Tuesday. But this is the final choice that you have, right? You can either have a node stable or unstable. You're going to have a center, and then I'm going to start looking at spirals in the next course or in the next lecture. Thank you. Problem sets on my desk, and you're free to go.